Welcome to my YouTube channel. I'm Arthur Francis Deban. Today we're going to be taking questions on determination of the degree of purity of a substance. Don't forget to subscribe and like, then so that you'll be able to get our subsequent videos. So, like I said earlier on, that we're going to take them part by part until the end of the whole thing. But today, which is purity and impurity, certain samples can be given to you for your titration, but they are corrupted with some impurities in them. So we have to determine the percentage purity or the impurity at the end of your titration. And when you do that, you have to proceed with your calculations to know the exact amount of purity or impurity. And I gave you various formulas. Percentage purity is mass count of pure sample over mass count of impure sample times 100. So permit me, I've written the given, so I will have to write or read the question for us so I will see how that correlates. Okay. Just have to edit the previous one. This one is small. Let's see which one again. Okay, the question says A is a 0.100 mole per gm cube HCl, Ca there. B contains 6.0 gram of a mixture of anhydrous sodium thiocarbonate 4 and sodium chloride in 1 gm cube of solution. The mass concentration of the impure aerosol. 25 cm portion of B. Yes. We require an average of 22.65 portion of A there. From the above data, we should calculate the amount in moles of sodium carbonate in 1 gm cube of B. That's the molar count. The amount is in mole. They now say in 1 gm cube of B, which is mole per dm cube. So you have to follow the question very well. So by so doing, we have to balance the equation and put down the variables 2:1, but we have to balance it to see how that works. How is it true that is that? So the equation of reaction is HCl plus disodium CO3. So this gives us sodium chloride plus H2O plus CO2 gas, liquid, aqueous, and aqueous. I have one hydrogen, I have two hydrogens. So if I put 2 here, I'll have 2 hydrogen. Okay, hydrogen is balanced for now, but chlorine here is 2, here is 1, sodium is 2, so I can put 2 here to balance that. Carbon and oxygen, carbon is okay, oxygen, we have 3 of them, so that is balanced. So that's the reason why I have number of moles of acid is 2, number of moles of base is 1. So I can take this out so that we can solve the question quickly. Now the first question says amount in moles of sodium thiocarbonate 4. So the molar concentration of the base A. Molar count of B. So for us to get the molar concentration of the base, we have virtually our CAVA NA, VB, NB. So we use the CAVA formula. So this is what we have. We use the formula CAVA over CBVB is equals to NA over NB. We're looking for CB, so CB is equals to CAVA NB over VB NA. And this is equals to, the CA is 0.100 mole per dm cube times volume of acid is 22.65 cm cube times number of moles of base NB is 1 all over volume of the base is 25 cm cube times number of moles of acid is 2. So this is equals to 0.100 times 22.65 equals to this, divide by 50 is equals to 0.0453. 0.0453 mole per gm cube. The cm will go, so the gm cube will be left. So I have my Cb now to be 0.0453 mole per gm cube. So that's A. B, the mass of sodium trioxocarbonate 4 in 250 cm of B. Okay, the mass, let's see that. I can take out this. B, mass of B in 250 cm cube. Now, from our little derivations, we say mass com is equals to mass over volume in dm cube. So the mass will cross multiply. So mass will be the mass concentration times the volume. So if I put that down, for us to get the mass now, it is obvious that for us to get the mass, we need our mass concentration. So now, if this is the formula of this we have now, mass com of B times volume of B. So that is the basic formula which we are going to use. But we don't know what the mass concentration is. So for us to get the mass concentration, let's proceed. Remember, this mass concentration 6.00 is that of impurity. So we can determine that of purity by making use of this variable here. So let's proceed. We want to get our mass concentration of the base. So let me call this BI. Mass com of B is molar com of B times relative molecular mass. The molar com of the base is 0.0453 times 106 G mole. This is the mole per gm cube, pardon me. So let's say that 0.0453 times 106. That's 4.80. So we have 4.80 GDM cube of B. This is that of purity. So I can put it where, GDM cube is equals to 4.80 GDM cube. Purity. So this one is that of the pure sample of sodium trioxocarbonate 4. They gave us that of impure. So we have gotten this. So we have to go back to the mass which they require of us with a volume of 250. So let's go back there to solve. I've gotten this already. So now the mass com is equals to, from our formula, 4.80 GDM cube times volume. For me to get my mass, so times volume, which is 250 over 1000. I have to convert it to be dm cube. Very important, don't forget that. So move on. So I have my 250 divided by 1000. This is 0.25. 4.80 GDM cube times 0.25 dm cube. My mass will be times 4.8, 1.2 gram. So now we have the mass which we'll be looking for. Next question says percentage by mass of sodium chloride in the mixture. Now the percentage of by mass of sodium chloride in the mixture, they are requiring the percentage in purity because the sodium chloride happens to be inside the salt. as an impurity, inside the sodium tricarbonate 4 as an impurity. So for us to determine that, they didn't ask us directly, but we should know. They are asking us of what? The percentage what? Impurity. So I've given us two formulas. Percentage purity is equals to the mass count of pure over impure times 100. Why? From there, we have percentage purity plus percentage impurity. Purity plus impurity equals to 100, where you make purity or impurity or whatever you're looking for the subject of the formula. So let's proceed. We're going to get our percentage purity first. Then we'll use the second formula to get that of what? Impurity. So C. C, percentage purity first, is equals to mass count of pure B. B is sodium tricarbonate 4 over mass count of impure B times 100. And let me give you also another hint. When your mass concentration of purity is higher than that of impurity, means you're wrong. The impurity consists of, that of impurity is made of the purity and some amount of impurity. So that one is supposed to be larger or bigger. So let's say that we are asked, it's okay. So this go on to give us mass count of pure B, which is 4.80 GDM cube over 6.000 GDM cube times 100. So the GDM cube will take themselves out. So this is equals to 4.8 divided by 6 times 100. So that's 80. So I have 80% purity. So if I have 80% purity and we say purity plus impurity equals to 100, what becomes impurity? Which is 100 minus purity is 20. So let's put that down. So purity is this. Okay, CI. Therefore, percentage purity plus percentage impurity equals to 100. We're looking for, we've gotten purity to be 100, 80. So 80% plus percentage impurity is equal to 100. Make this the subject. So become percentage impurity is equal to 100 minus 80. Percentage impurity is equal to 20%. So that is the end of that question. So always take note that purity of substances and impurity of substances require a great deal of your understanding of volumetric analysis calculations. Otherwise, you may flop along the line if you're not careful with the formulas or what comes in and out. Let's take our next question. They say we should put a 0.019 mole per dm cube KMnO4, that is potassium tetraozomanganate 7, solution in the burette. 25 cm cube of that of 6.0 GDM cube of impure ethane dioic acid. Solution is titrated against 23.5 of KMnO4. If the equation of reaction is this, we should calculate on and on. So this time around, the calculation is based on redox. This is redox titration calculations. So the balancing of redox equation, many a time is always given, but if it is not given, you know how to balance it. In subsequent classes, or class to come, I will show you how to balance your redox equation, so that when situations arises that it is necessarily needed, you have to apply your knowledge of it. Let's take the given. So this time around we are dealing with oxidizing agent and reducing agent. So we are not going to be calling them directly the way they are. So oxidizing and reducing agent. So let's go on. Okay, our A, let's call it A, is our oxidizing agent, KMnO4. Let's say concentration of oxidizing agent is 0.019 mole per dm3. Okay, for 25 of this, the reducing agent, let's call that B, is did I give it to us? Ethanediol acid, C2O4. Volume of, okay, let's call it volume of reducing agent is 25 cm3. Now, 23 of KMnO4, the volume of oxidizing agent is 23.5 cm3. If the equation of reaction is this, so from the equation of reaction we'll be able to get, now we don't know the concentration of reducing agent. We don't know. So let's see the equation of reaction so that we'll be able to get our number of oxidizing agent and the number of reducing agent. So let's proceed. The equation of reaction is 2MnO4 minus plus 5C2O4 2 minus plus 4 hydrogen ion gives us 2Mn 2 plus 10 CO2 plus 8 moles of water. Okay, that's balanced there. So let's take the number of moles of the oxidizing agent is 2. The number of moles of the reducing agent is 5. Okay, from here they say we should calculate the concentration of the reducing agent. Concentration of the reducing agent. That's what they are asking us to do. So, if I have to take out the equation of reaction, okay, let me just start this way first. We have concentration of oxidizing agent times volume of oxidizing agent over concentration of reducing agent times volume of reducing agent is equals to number of moles of oxidizing agent over numbers of moles of reducing agent. So this is equals to, we are looking for the concentration of the reducing agent, the C subscript RA is equals to, here we now have concentration of oxidizing agent times volume of oxidizing agent times number of moles of reducing agent over volume of reducing agent times number of moles of reducing agent. Okay, I'm saying reducing agent here twice. Let me check it again. Sorry, I'm taking this out. This. Oh, volume of reducing agent times number of moles of oxidizing agent. So this is oxidizing agent. So this is equals to, let's substitute, concentration of oxidizing agent is 0.019 mole per dm3 times volume of oxidizing agent is 23.5 cm3 times number of moles of reducing agent reducing agent is 5 all over volume of reducing agent. Reducing agent here, the volume is 25 cm cube times number of moles of oxidizing agent is 2. So our cm cube will cancel cm cube, we're left with gm cube. So this is equals to 0.019 times 23.5 times 5 is equals to 2.2325 divided by 50 is equals 0.04465. So now I have 0.04465. Let's call that 7 mole per gm cube. So this is the concentration of reducing agent, 0.0447 mole per gm cube. Next question here. What did I require? They say, okay, we're done with A. Let's look at B. Mass con of reducing agent in GDMQ. Okay, reducing agent, which is this, we have to get the mass con. Then percentage purity. Something is lacking about the question. Let me go through it. We've not seen the mass con. Okay, they gave us, sorry, I didn't spot it out. They gave us 6.0 GDM cube of impure ethane dioxide acid. So ethane dioxide acid impure GDM cube of impure ethane dioxide acid is 6.0 GDM cube. And now we can proceed. They want us to get, which is our II, mass con of the reducing agent. So that is of the purity. So let's take that. I can clean this. II, mass con of reducing agent is equals to molar con of reducing agent times relative molecular mass of reducing agent. Now, we have to calculate the relative molecular mass of that. So let's proceed. Take out more. Now, the molar con of reducing agent is 0.0447 mole per gm cube times relative molecular mass of H2C2O4. Alright, this is 0.0447 mole per gm cube times, this is 1 times 2 is 2 plus, carbon is 12 times 2, 24 plus, oxygen is 16 times 4, 64. Okay, and this is equals to 0.0447 mole per gm cube times 26 plus 64 is 90. So that's 90 G mole is a unit. Now this is equals to 90 times this times 0.0447 is equals to 4.023. 4.023 GDM cube. This is the mass con of pure. So let me put it here. GDM cube of pure ethane dioxide acid is 4.023 GDM cube. Next question. They say We should calculate the percentage purity of a diode acid. Okay, let me clean all this. The third one is the third question is percentage purity of reducing agent is equals to mass comm of pure reducing agent, that's a diode acid, over mass comm of impure reducing agent, which is the diode acid times 100. And this is equals to 4.023 GDM cube over 6.0 GDM cube times 100, and that would be equals to that's 67.05. 67.05% purity. So if that is our purity, impurity is 100 minus that. So what do we get? 32.95. So percentage impurity will be 32.95, while the percentage purity is 67.05. Okay, let's take it down. IV, percentage impurity, is equals to is equals to 100 minus purity percentage, and this is 100 minus 67.05%, and this is 20 what? 32.95. 32.95% or 33% approximately. We're done with our second question. Let's look at the fourth question. The third, sorry.